Good evening to one and all. I welcome you all to the sixth and final keynote lecture of SECON 21. Now, before we begin, I request all of you to please switch on your videos and mute your audios till the end of the session. I now welcome Divya S. to address the gathering and to introduce our keynote speaker.
Thank you, Sanika. A warm welcome to everyone present here. With great honor, welcome to the sixth keynote lecture of SECON 21 by Professor Usama Ebead on sustainability of reinforced concrete structures. I welcome the audience who has graced the event with their presence. With great pleasure, I would like to give a brief introduction on our chair, Professor Usama Ebead. Professor Usama Ali Ebead, Professor of Qatar University, is an internationally recognized expert in the fields of infrastructure renovation and strengthening, advanced composite materials, and numerical modeling. He has developed innovative strengthening techniques and finite element models for reinforced concrete structures. He has been carrying out innovative and significant research on the use of non-corrosive reinforcements in concrete combined with byproduct materials and construction waste. He is currently the editor of Structures and Buildings Journal and reviewer of several scientific papers in journals and conferences and reviewer of research proposals. Professor Usama is the chair of the Department Curriculum Committee at Qatar University. He is currently a member of ACI Committee 549. He has received 18 funded research grants of approximately 2.7 Canadian dollars. He has published 43 in-text journal papers and over 46 referred conference papers. Dr. Usama has been a dedicated teacher as recognized by the appreciation of the students and the college. He has received 2 teaching awards for his excellence in teaching in both 2015 and 16. Over to the keynote lecture.
Good morning, ladies and gentlemen. My name is Professor Usama Ebead. I'm a professor of structural engineering in Qatar University. It is my pleasure to give this keynote speech. Let me share with you my presentation. The speech is entitled Sustainability of Reinforced Concrete Structures for the International Conference on Structural Engineering and Construction Management. I'm very glad that I am giving this speech, although I hope that it would have been delivered in better circumstances. I wish you all best of health and please keep safe. I will start in a minute now my presentation. Let me just set timer here. All right. The speech is outlined to the following: a background, problem statement, research objectives and significance, research outline. I'm going to show the materials and methods used. Then we'll talk about results and discussion. Then we'll draw some conclusions and future recommendations. Concrete as a material is the most commonly used in construction worldwide. While it is typically produced by mixing cement, fresh water, natural aggregate, and mixtures as well. Fresh water is not only used for mixing concrete here, but it's also used for washing aggregates and concrete curing as well. Conventionally, steel bars are used to reinforce concrete in tension, and reinforced concrete structures are currently the most commonly used type of buildings and infrastructure in human civilization. Recently, fiber reinforced polymers, FRP composites, have emerged as an alternative reinforcement material. It typically consists of fibers and polymer matrix. The fibers like carbon fiber, aramid, basalt, glass, and the polymer matrix typically like epoxy, vinyl ester. Glass fiber reinforced polymer bars are the most common in reinforcement applications because it has acceptable mechanical properties. Also, it has significant lower cost compared to other FRP bars. So we're talking here about this type, in particular, glass FRP versus other types of FRPs. There are advantages of using FRP reinforcement because it has high strength to low weight ratio. It has non-corrosive characteristics and non-magnetization properties. But there are some challenges associated with the use of FRP reinforcement, and these are mainly due to its higher initial cost, lower elastic stiffness, linear elastic brittle failure. It has also some concerns with fire resistance. However, Canadian Standard Association 806 and American Concrete Institute Committee 440 have both adopted concrete glass FRP or concrete with glass FRP reinforcement, and they produce these standards as guidance for the use of GFRP in concrete construction. Also, it has been accepted by contractors and municipalities. Some projects have already been constructed using FRP, and these are only a few examples in Canada, like a parking garage and a pedestrian bridge or trail bridge. All these examples are in Canada with these references here. Let me talk about the problem now. What's the problem that we're facing? We have a number of problems. First is the freshwater scarcity. Around 2/3 of the global population live under conditions of severe water scarcity for at least 1 month per year. The construction industry alone uses over 2 billion tons of fresh water every year to produce concrete. Qatar, as an example of a country that lacks fresh water, it uses 99% of its fresh water coming from desalinated water or desalinated seawater. The desalinated or desalination industry is very expensive and leads to greenhouse emission or CO2 emissions, as well as the brine disposal challenges. So one potential step is to use seawater. An important step towards sustainability is reducing to the extent possible the use of fresh water in concrete production. Seawater may represent a valid alternative to fresh water in concrete production. The use of seawater in the concrete mix is currently prohibited, actually, and that's why we're doing this research. And this is mainly due to the high presence of chloride ions, potentially leading to inevitable steel reinforcement corrosion. And this issue now can be mitigated. How? By using an alternative reinforcement that doesn't corrode, like FRP reinforcement bars. A second problem this research addresses is the possible depletion of natural aggregates. In fact, the global construction industry consumes over 4 billion tons of natural aggregates every year. The third problem, which is the disposal of construction and demolition wastes. C&M wastes make about 30% of the total waste worldwide, of which approximately 50% is coming primarily from concrete. A potential step here is to why not recycling concrete aggregate? Why not using recycled concrete aggregate in construction industry? In fact, using RCA can mitigate the negative impact of construction and development waste, as well as harvesting the natural aggregates. There are some characteristics with RCA. It's more porous, it's less dense, and it has higher water absorption characteristics. The challenges associated with the use of RCA, first, it reduced the concrete workability. This actually can be addressed and mitigated by using superplasticizer or by using RCA in a standard saturated surface dry condition. It also, another challenge associated with RCA, it has inferior mechanical properties of hardened concrete. And this can be addressed by reducing the water cement ratio than that needed for natural aggregate concrete. You can look here at this relationship between the compressive strength and the cement content for both mixes. One uses recycled aggregate and one uses natural aggregate. You can see that increasing the cement content from like 313 kilogram per meter cube to 330 can result in reaching the same compressive strength here. A third challenge with the use of RCA is the possibility for being salt contaminated, which leads to steel corrosion. Again, for this we can use FRP. Excuse me. In conclusion, regarding the problem statements here,
according to Wikipedia, a problem
the existing literature postulates that salt existing either in seawater or possibly in RCA has no significant negative effects on plain concrete characteristics. Also, the negative effect of using seawater appears to be limited to the corrosion of steel reinforcement. For this, FRP represents a valid alternative non-corrosive material for concrete reinforcement. So the research objectives is after sustainable concrete. And this can be done by combining seawater, solving partially some of the problem associated with the excessive use of freshwater, plus recycled concrete aggregate, solving the issue of disposal of recycled concrete aggregate, and accompanying this the FRP reinforcement that is corrosion-free to come up with sustainable concrete. This flow chart here, it showed some scenarios when using conventional concrete and what is the problem that's associated with them and how can we overcome that using, in light of the proposed or in light of the work that is being done here. So here, conventional concrete requires steel reinforcement, but the challenges here is that steel reinforcement can corrode. Then, instead of using steel corrosion, steel reinforcement that is corroded, we can use FRP reinforcement. It has a challenge of initial high cost with proper life cycle cost analysis and life cycle assessment. We can reach concrete with FRP as a sustainable material. Looking here, when using the coarse and fine aggregate, the challenges here when using coarse and fine aggregates, the challenge is that we need to preserve natural aggregate resources, and also we need to reduce construction and development waste, construction and demolition waste. And here we use RCA. But the problem here, again, it has possible chloride contamination leading to corrosion of steel reinforcement. For this, we use FRP reinforcement again, leading to sustainable concrete. Conventional concrete also uses fresh water, and the challenge here is that we are facing freshwater scarcity. So, and also desalination has certain environmental impacts. So instead of fresh water, we can use seawater in the mix, but again, it's full of chlorides, leading to challenges again of steel corrosion, leads to using FRP again for sustainable concrete. So the solution here, if we would like to use sustainable concrete that uses seawater, recycled coarse aggregate, and FRP, this is a combination. This is the right combination for sustainable green concrete in lieu of freshwater, natural aggregate, and steel reinforcement type of concrete. So the research outline is divided into 3 parts. The first part, we do some concrete characterization. The second, we do actual beam testing. And the third part of the study is conducting life cycle cost analysis. And we're going to present these studies or these parts here as part of actual published studies, the titles of which would be given at the end of this presentation. For these studies, we can divide it into 2 main components: the experimental investigation and cost effectiveness. The experimental tests conducted on plain and forced concrete to verify the structural safety and proposed combinations. And the cost effectiveness is done through life cycle cost analysis to demonstrate the economic viability of the proposed combination. The combination we're talking about, again, is Seawater, RCA, and FRP. For doing this, we created 3 mixes. Mix A, B, and C. We'll be using these throughout the presentation. Mix A, it uses fresh water, and the type of coarse aggregate is conventional. Mix B, it uses seawater, also coarse aggregate conventional. And mix C, it uses seawater, and the type of coarse aggregate is the recycled coarse aggregate. All right, I'd like just to keep track of time. The structural behavior of plain as well as reinforced concrete is compared, considering 3 concrete mixes. In all these 3 mixes, we use blast furnace slag in all admixtures as supplementary cementitious material, and it constituted about 65% Portland cement replacement level. The curing conditions also differs. We have standard curing conditions. We call it E1 in our study here, where concrete specimens were cured in fresh water for 28 days and then left to be exposed to the outdoor or ambient environment of Qatar. The second condition, E2, is the seawater immersion, and where we actually exposed the specimens to harsh environment of seawater that immersed the specimens in seawater in fiberglass tank until testing time. And the specimens were tested at different ages up to 1 year following casting. We conducted for studies 1 and 2, we conducted tests on plain concrete. These are the typical slump test, density, yield, air content according to ASTM standards. Also, we conducted mechanical characterization tests, typically the compressive test and shrinkage test, as shown here. Also, for studies 1 and 2, we conducted the rapid, the permeability performance of the hardened concrete using RCP, rapid chloride permeability test, and also the water absorption test. We also conducted the isothermal calorimetry in studies 1 and 2. We also did the heat flow, and that is measured 7 days following the mixing and normalized to the mass of the cementitious material. We tested also the microstructural behavior of the specimens. We used the scanning electron microscopy, which was performed in accordance with ASTM standards. We actually considered 3 types of analysis techniques, namely the secondary electron imaging, backscattered electron imaging, and energy dispersive X-ray microanalysis. In study number 3, we actually tested like on macro scale reinforced concrete beams, actual reinforced concrete beams. We used two variables for these beams, namely the concrete mixtures, mix A, B, and C. We already defined those. And also the type of reinforcement. We tested specimens with all steel and all GFRP. When we say all, we mean longitudinal reinforcement in the tension side and the compression side, and also the stirrups. You would notice here that we tested 3 sets of specimens. Each set of specimens includes 2 specimens to improve the reliability of the readings. And this is the layout of the details. The steel reinforcement, we're talking about a specimen of 200 2 meter, 200 centimeter, as a millimeter. And we talk here about specimen 4-point loaded, as shown here. We used 8 millimeter stirrups and top reinforcement, and the clear cover was maintained at 25 millimeter level. This is a test setup that shows the type of instruments used for measuring different deflection cracks, crack widths, and strains. As for the second part of the study and materials and method, we used the life cycle cost analysis, and these are used for studies 4 and 5. And in these 2 studies, we use the life cycle cost analysis that has components, 4 main components. The first is the material component. In our study, we're talking about the material production and supply. For example, here the concrete and reinforcement bars. The construction as the second component, which includes material transport, concrete formwork, casting of the concrete, placement of the reinforcement, and waste disposal. Repair, the third component of the life cycle cost analysis. This includes periodic inspections, minor concrete repairs, corrosion-induced damages, reconstruction if needed. And the fourth component of the life cycle cost analysis is the end of life. And this includes typically demolition, disposal, replace, landfill, and so on. The life cycle cost analysis in studies 4 and 5, we use the unit costs. We obtain these unit costs using the RS means online software or data set. And also we used previous publications for coming up with the unit costs. Also, the service lives and maintenance periods were estimated according to or using Life 365 software. In this study, we considered a 100-year study period, and the net present cost in PC was determined considering a discount rate of R, according to this equation. Now let's talk about some results. First, let's start with the study number 1, which is an important study on the fresh and hardened properties of seawater mixed concrete. In this study, we had the first 2 mixes, mix A and mix B. And you can see from this relationship between slump flow on the vertical axis and time that mix B was approximately 20% lower than mix A in terms of the initial slump flow value. And this is actually an accelerating effect from seawater ions. However, the seawater has no effect actually on the density, yield, and air content measurements of the fresh concrete. So the difference was actually noticeable mainly in the initial slump flow. As for the hardened concrete, it was interesting to see that the seawater, either in environment E1 or environment E2, showed slight increase in the compressive strength in the first until in the first 7 days following mixing. And this is probably due to the accelerating effects from the seawater ions. Later than that, there was a reduction of 7 to 10%. Look at here, observed in the compressive strength of mixed B in the long term due to leaching of hydrates. In study 1 also, we looked at the hardened concrete properties in terms of shrinkage, and as you can see, there was barely any difference between shrinkage measurements for mixes A and B. Also, using seawater in concrete mixes has almost no effect on the permeability and resistance to chloride ingression of hardening concrete. The two mixtures under comparison, mixes A and B, had similar results in terms of the rapid chloride permeability and water absorption as per the results here. As for the isothermal calorimetry, the heat released, the rate of hydration of the seawater paste was higher than that of freshwater paste at early ages, up to 7 days, as seen here. At late ages, the heat release was almost the same for both cement pastes. The microstructural investigation conducted on study number 1 using scanning electron microscopy revealed a more densified microstructure of the seawater paste at early ages compared to fresh water paste. However, at later ages, the microstructure was similar for both pastes. Also, the crystalline products were observed in concrete mixes or mixed with seawater, suggesting that part of the calcium in the pore solution reacted with the sulfate ions to form such phases, mostly gypsum, as per the EDX measurements. While not directly confirmed, gypsum formation could possibly yield to expansive crystallization pressures that result in decreases in concrete strength. Now, we can see that fresh concrete, as expected, would say, overperformed, freshwater concrete overperformed seawater concrete. So with this, we introduced remedial measures. These remedial measures may overcome the drawbacks of using seawater in concrete. So using chemical admixtures in seawater concrete helped improve the concrete properties of mix B. Here, we propose adding 0.25 liter per meter cube of a commercial retarder and increasing the superplasticizer amount by 15%. And when doing this, when measuring the two main characteristics that has significant, let's say, some difference, these are the slump flow and the compressive strength, you can see with the remedial measures, we have reached the same level of natural or concrete made with natural water or fresh water. In study number 2, we actually studied the performance of seawater mixed recycled aggregate concrete. So in study number 1, we didn't use the recycled aggregate concrete. In study number 2, we used the mixed recycled aggregate concrete to focus on the effect of this. So this study compared again two concrete mixes, namely now the concrete mix A, which is considered a reference where we use freshwater concrete and natural aggregate with mix C that uses seawater mixed recycled aggregate concrete. Looking here at the result of the slump flow, combining seawater and RCA reduced the concrete density about 5% and increased the air content of the fresh concrete. And combining seawater and RCA reduced the slump flow by about 25%, and the workability tension mix C remained flowable for only half the time as mix A. RCA has harsh or granular texture because of the adhered porous mortar. More water or efforts is required for compaction due to the interparticle friction in RCA concrete. As for hardening concrete characteristics, when combining seawater and RCA, this results in a significant reduction actually in the strength gain of hardening concrete of approximately 35% almost at all ages. Long-term seawater curing up to 1 year increased the compressive strength of hardening concrete because of the ongoing hydration. Mix C showed slightly an increase in the drying shrinkage of approximately 10% compared to mix A, mostly due to the effects of the RCA. Also, combining the seawater and RCA results in a reduced permeability performance, evidently from the higher charge passed and water absorption of mix C. Although most of the measures are in the favor of using recycled aggregate concrete, but there are still remedial measures can be done to improve the performance of mix C. So mixtures design modifications were proposed to overcome the performance issues of mix C using chemical admixtures and also reducing water cement ratio, as can be seen here for the slump flow measurements and for the compressive strength measurements. It's not as still perfect, but like for the sake of like use of RCA with these remedial measures, we still can find these results really attractive. Study number 3, we studied the combination of seawater and recycled aggregate in actual beam, reinforced concrete beam, combined of course with FRE bars. So we constructed 12 reinforced concrete beams tested under 4-point loading. 3 test variables were used: the mixing water, either seawater or freshwater, aggregate type, either natural or virgin or recycled, and the reinforcement material, either regular black steel or GFRP bars. All right. If reductions in concrete performance are averted using admixtures and or changes in concrete mix design, using seawater and recycled coarse aggregate in concrete mixtures has little to no effect on the short-term flexure capacity of RC beams. The reinforcement material control the flexure performance of reinforced concrete beams. Look at the failure mode here. The steel reinforced concrete beams failed due to concrete crushing followed by concrete yielding, which is typical. For the GFRP reinforced concrete beams showed a more brittle failure due to rebar tensile rupture. For low deflection behavior, as can be seen here in these 2 graphs, for steel reinforced beams and FRP reinforced beams, you can definitely realize that can gain higher loads in case of FRP but lower ductility. So GFRP reinforced concrete beams show approximately 25% increase in ultimate load, and GFRP bars showed approximately 25% lower deflection than those steel reinforcement, as per the visual comparison between these 2 graphs here. There is an idealization of the load deflection diagrams enables us for theoretically study the behavior of both steel reinforced concrete beams or GFR reinforced concrete beams. Based on the behavior shown here, we can idealize the steel reinforced concrete beams passing through these three zones, but in case of GFRP, it only has two zones. In terms of the strain characteristics, the steel reinforced concrete beams had epsilon T max, maximum tensile strain values higher than the yield strain of 0.27% at failure. It's actually about 1.59% on average, associated with high compressive strains of concrete strain of 0.27% on average. For GFRP, these values were 1.8% on average, have exceeded the ultimate strain value of epsilon ultimate of 1.7%, and were associated with relatively lower concrete strain values of 0.16% on average. For the cracking behavior, this shows a comparison between these two beams at failure. One steel reinforced and the other with GFRP reinforced. Both steel and GFRP reinforced beams showed the same flexural shear crack pattern that is naturally expected for an RC beam subjected to 4-point loading. However, steel reinforced concrete beams had generally a greater number of cracks at failure. The crack width is, or the crack width values for at failure of steel reinforced concrete beams was 4 meters, were higher than those of GFRP reinforced counterparts, which are of 1.7 millimeter. This is because steel yields at the crack location, allowing for cracks to widen, of course. We did, based on the idealization of the behavior of both types of beams, we did some theoretical formulation based on the ACI code equations. The theoretical values of flexural capacity, deflection, and crack widths were predicted for the tested specimens and compared with the experimental results. A reasonable agreement was obtained between the predicted and experimental values of flexural capacity. The difference was about 7.5% in average. The ACI 440 is overestimated the crack widths for GFRP reinforced concrete beams, 0.9 millimeter predicted compared to 0.6 millimeter measured, probably due to the conservative use of bond coefficient of KB equal 1.4. The predicted deflections of GFRP reinforced concrete beams somewhat conformed with the experimental values. Only the difference was about 13%. Now, study number 4, it handles the life cycle cost analysis for seawater mixed concrete. In that study, the economic impact of combining seawater recycled coarse aggregate and GFRP was investigated through a CA of 2 design alternatives of the same structure. The use of alternative materials for concrete mix has no significant impact on the direct concrete cost and thus the life cycle cost performance. The cost savings are mainly influenced by the selection of the reinforcement material. So, in fact, the concrete, whether concrete made by the concrete reinforcement, either steel or GFRP, was actually the main making the main difference in cost. The use of GFRP reinforcement improves the long-term economic performance of structural concrete, as per this table here in these measures. Based on a 100-year study period and a 0.7% discount rate, the life cycle cost of the proposed design alternative, RC2, is approximately 50% less than that of the traditional reinforced concrete or alternative RC1, with a payback period of 20 to 30%, which is very interesting. The life cycle cost analysis outputs are highly sensitive to the choice of the discount rate, as you can see here. At a discount rate of 5.9 or higher, the life cycle cost of option or alternative RC1 over 100-year study period considered is lower than RC2. In study number 5, we actually did the cost effectiveness of reinforced concrete alternatives also for concrete. The life cycle cost analysis was performed on actual reinforced concrete water chlorination tank with different reinforcement: black steel, epoxy coated steel, stainless steel, and GFRP. The epoxy coated steel alternative had 11% lower NPC compared to black steel. Stainless steel achieved 25% lower NPC compared to black steel. The GFRP reinforced concrete achieved the best cost performance with 43% lower NPC. Stainless steel outperformed the conventional steel after 50 years following initial construction. Reconstruction at year 65 was also the break-even point between stainless and epoxy coated steel reinforcement, as seen here. GFRP achieved a lower NPC at year 35 following construction due to corrosion repairs. Well, I almost reached the end of my presentation, but first I'd like to give some conclusion and future recommendation. The results of these 5 studies suggest the potential use of the proposed combination of seawater, recycled coarse aggregate, and GFRP bars to produce safe, economic, and sustainable concrete structures. The current research, or this research that I just presented, represents a step forward towards completely verifying the proposed combination from technical, economic, and environmental standpoints. Based on the limitations of this research, the following topics are encouraged for future studies. In fact, I'm currently working on this research through other projects, like the use of other advanced materials like basalt FRP in the proposed combination instead of GFRP, or besides FRP. Studying the shear behavior of seawater mix recycled aggregate GFRP reinforced concrete, like in addition to study that we did in the flexure performance, why not study also the shear performance? Also the long-term durability performance of the proposed concrete. The study that we presented was limited to 1 year. Why not studying this for like 3-4 years? Also, the life cycle assessment studies can also be performed. Here, giving this slide showing the titles of the main 5 publications that I based my speech upon. Please feel free to go and have a look at these papers. In case you would like me to send this paper, please don't hesitate to contact me by email, which is actually can be given to you by the conference people. At the end here, I'd like to thank you. I'd like to acknowledge very important people. I'd like to acknowledge Dr. Adel Younis. He's the former PhD student whose research was actually on this topic. I'd like to acknowledge the fund provided by Qatar National Research Fund I'd like to acknowledge ATP Construction Composites Company in Italy and Ready Mix Concrete Qatar. With this, I end my presentation. I'd like to thank you very much. I hope that I would have been available to you, but unfortunately at the time I'm giving the presentation, I'm in Canada, and it would be very difficult to give this live. Therefore, I opted for recording this presentation. Again, thank you very much, and all the best. Please keep safe.
Unfortunately, Usama sir couldn't join us today, but we will definitely pass these questions to him and will let you know the answers soon. Now, the link of the feedback form will be available in the chat box soon. Participants, please make sure that you fill it so that you can receive your certificates. I now call upon Shweta Maria Charles to deliver the vote of thanks.
Thank you, Sanega. It was indeed a great privilege to have Professor Usama Ebead, Professor of Structural Engineering and Chair of the Departmental Curriculum Committee at Qatar University, as the keynote speaker today. Even in his absence, I would like to take this opportunity to thank him for enlightening us and sparing his precious time to record a video on the topic Sustainability of Reinforced Concrete Structures. It gave us deep insights on a better mixture for reinforced concrete and also revealed some interesting facts. Today, we had the opportunity to hear your thoughts, and hopefully, this will encourage us in our future ventures. Once again, I thank you, sir, for having spared your precious time for all of us. Thank you so much. With deep sense of inspiration, I thank our HOD, Dr. Unnikarta Ji sir, and all the teachers for their untiring efforts. Our sincere gratitude goes out to ASC FISAT and all the associated organizations who really worked hard to make this event successful. Also, I thank each one of you for gracing the event with your presence. Once again, thank you all. Stay home, stay safe. By this, we have come to the end of the session. Thank you for being a part of it.
Thank you all for joining. Participants may please leave the meeting now. The problem with the link will be soon solved. Participants, please wait for a few minutes.
Link is active.